Hello and welcome to the session on the strength of material. In this session, we will be discussing with temperature, stresses and strain. I am Professor V V Khond, working with the Mechanical Engineering Department at KK Institute of Engineering, Education and Research, NASA. So, to start the session, so what is thermal stresses? So, these are the stresses which are induced in the body due to the change in the temperature. When the temperature of body is raised or lowered, the body has a tendency to expand or contract freely. In such cases, no thermal stresses will be induced in the body. But if the body is prevented from expansion or contraction, then the thermal stresses are developed in the body. So let us take a case of simple member having the length L, which is fixed at one end, free at another end. So if the member is being heated with the temperature rise T, in that case there will be certain expansion. Okay, so expansion of the member will be dl. In this case, expansion of member will be dl, but and there is no thermal stresses that is generated. So that is the case. Now for this particular case, if the rod is free to expand, then the free expansion is given by dl is equal to alpha into T into L. So where alpha is the coefficient of linear expansion, whereas T is the rise in the temperature. So if you take the case of strain, in that case that will be change in the length upon original length, that will be equal to alpha TL, that is the change in length upon original length L. So it comes to be alpha into T. Now for the temperature stresses, so that body has to be prevented. So the expansion has to be prevented. So whatever these are, if you are putting the support over here, that means whatever the expansion that is being prevented. So expansion is being prevented. In that case, the thermal stresses will get developed. So how to get that particular thermal stresses? So for thermal stresses, so initially thermal strain, let us say the expansion prevented upon the original length. So expansion prevented will be equal to alpha into T into L. So whatever the expansion of the bar that is being prevented upon the original length is equal to alpha into T. So thermal stress will be equal to thermal strain multiplied by E, that is equal to alpha into T into E. So whenever it is a thermal stress, the generalized formula is equal to alpha into T into E. T is the rise in the temperature. Now the case is like that. Now whatever the supports that are being yielded, if the support yield by delta L, that means we are allowing for some expansion by um, by by moving the support. So for in that case some extension will be there and the thermal stresses will be developed. So for such cases, thermal strain will be equal to expansion prevented, that is alpha TL overall length minus delta L. We are allowing the expansion, so this is expansion prevented upon the original length. So we are having the formula thermal stress is equal to thermal strain multiplied by E. So this is what the formula alpha TL minus delta L upon L into E. Okay. Now take the case of the thermal stresses in the composite bar. So for the case of composite bar, let us take the case of the two bars, that is brass and the steel. These are the two bars. These are being composite. So it is being joined over here. It is joined being this here. Now this is the case before heating. Now if you heat the bar, in that case, let us take for the sake of convenience. So the brass will freely expand up to this point, and the steel will freely expand up to this particular point. Okay, so that is the free expansion of brass, free expansion of steel. So free expansion of brass will be delta B, free expansion of steel will be equal to delta S. Okay. Now as the coefficient of linear expansion of brass is more than that of steel, the brass will expand more than that of steel. So that's why it is being shown delta B greater than delta S. So now as it is a composite section, it is a composite section. In that case, what happens? So uh, brass will try to pull the steel in this direction, rightward direction, while the steel having less expansion will try to pull the brass in the leftward direction. So in that case, what will happen? That is, there will be compression in the brass and tension in the steel. So brass there will be compression because of the steel will try to pull towards the left direction, and in the tension in steel because the brass will try to pull the steel bar in rightward direction. Because of that, we are having the actual deformation. So this is actual deformation considering the composite section. Now, for the calculation purpose, we are taking actual expansion of brass will be equal to actual expansion of steel. So let us take the case of load on the brass. That is, load will be equal to stress multiplied by the area. Load on the steel will be equal to sigma s multiplied by a of the area of the steel. So stresses in the bar sigma b, stresses in the steel, that is sigma s. Now actual expansion of steel will be equal to free expansion of the steel due to temperature plus expansion due to tensile stress in the steel due to the composite section. So first case is related with the temperature and the second plus is related with the composite section. So plus because there are the tensile stresses in the steel. So sigma s, that is the strain, this is the strain multiplied by the original length. So that becomes the deformation. Okay. Now actual expansion of copper will be equal to free expansion of copper minus contraction due to compressive stress induced in the brass. In this case, in the first case it is expansion. Now in the second case it is contraction. So that's why it is minus, here it is plus. So actual expansion of steel will be equal to actual expansion of brass. Now comparing these two, we will be having the formula alpha s T L plus sigma s by Es into L is equal to alpha b T into L minus sigma b by Eb into L. So removing the length from each of the points, we will be having the removing the original length. This can be cancelled out, this can be cancelled out, L can be cancelled out. After cancelling L, we will be having alpha s into T plus sigma s by Es is equal to alpha b into T minus sigma b upon Eb. Now we'll solve one numerical. So in that case, we'll be having a rigid block AB weighing 180 kilonewton is supported by 3 rods symmetrically placed as shown. Before attaching the weight, the lower ends of the rod are set at the same level. The areas of the cross section of the steel and the copper rods are 800 mm square and 1350 mm square respectively. Determine the stresses in the rods if the temperature is raised by 25 degrees Celsius. Second, the temperature rise for no stress in the copper rod. So this is being given, two steel rod and one copper rod is being given. Their lengths are different. So it is being, so it is a case of the composite section. It is a case of the temperature rise, and it is a case of generalized loading. So loading is 180 kilonewton, that is the loading, and the particulars are being given EC, that is modulus of elasticity for copper, modulus of elasticity for steel, that is being given alpha coefficient of linear expansion for copper, coefficient of linear expansion for steel. So you can see the two values alpha C and alpha S. So this value is more 18, this value is more, so the expansion of copper will be more than that of steel. So total elongation of each rod is equal to elongation due to temperature plus elongation due to load. So we have to consider both the cases, elongation due to temperature plus elongation due to load. So free expansion of copper is more than that of steel. So alpha C value is more than that of alpha S. So compressive stresses induced in the copper and tensile stresses induced in the steel because of the more expansion. So copper will try to pull, and copper will try to pull in the downward direction, while steel will try to pull in the upward direction. So that is what thing. So this is the equation that we have. So in the previous case, L, there are the lengths are same, so that's why we are able to cancel out the length. But here the lengths are different. So alpha s ls t plus ps ls upon as es is equal to alpha c lc t into t minus pc lc upon a into ac into ec. So alpha, that is coefficient of linear expansion, t is the rise in temperature. So we are putting the values over here. So putting the values, value of T 25, value of L 1200, value of alpha S, this is the value of alpha C, value of LC, value of T, PC not known to you, PAPS not known to you, because these are different values. So we are supposed to calculate the PS and PC. So we can get the equation, generalized equation, PS is equal to 65,601 minus 1.918 into PC. So this is the first equation we get. Now what we want is another equation. So another equation we can get from the equilibrium equation. So that is the thing. So twice PS plus PC is equal to 180,000 Newton. Okay. So whatever the load that is being shared by 2 steel and 1 copper rod. So after solving the equations 1 and 2, we can get the value of load in the copper and load in the steel. So load in the copper is compressive, load in the steel is tensile. So from the load, we can easily calculate the stresses in copper and stresses in steel. So stresses in copper, load upon area. So this is the load upon area of copper that is being given, and the load in the stresses in the steel. So load upon area, that is the value. Okay. Now we are going to solve another value, requirement, as there is no stresses in and hence no load in the copper rod. Sigma c will be equal to 0. Hence load in each rod is equal to 90,000 in the steel rod. So we are not considering the load in the copper rod. So sigma c will be equal to 0. So load in the each rod will be equal to 90,000 Newton. Okay. So taking the previous equations, only thing the change is P you have to calculate, PS that is not known to you, and PC that will be considered as 0. Load in the copper rod that should be taken as 0. That is another case. Okay. So by putting the values and calculation for the T. So calculation for the T will be coming as 34.3 degrees Celsius. So this is the temperature rise when there is no load in the copper rod, and load in each rod for the steel will be equal to 90,000. Okay. So in the conclusion we can say, whenever there is a case of thermal stresses, you have to consider the rise in temperature. So that will be considered as alpha into T into L, that is the free expansion. Then if it is a case of composite section, then you have to consider the compressive stresses and tensile stresses in each section. And the third is, if there is combined loading, that also we have to consider. So the three cases have to be considered. So the reference is Strength of Material by H.S. Ratan book and Strength of Material by R.K. Bansal book. So thank you for watching the video. If you like this video, then like it. Also please subscribe my YouTube channel by pressing the bell icon button and never miss the updates. So thank you.